So far in introducing functions as equations, we've seen them in the form of just a single expression. So for instance, we may have seen something like f of x equal to 3x squared plus x minus 5, where we have the name of the function on the left, the input in parentheses, and the expression that determines how the input is going to be evaluated, the process that is going to turn the input into the output. And on that right-hand side is just built on a single expression which applies to all values of x. Now, this covers a wide range of functions, but it's not all of them. It's not the whole story. There are functions that for certain values of x may require a certain expression, but for other values of x might require a different expression. And so for different parts of the domain, they might evaluate those inputs differently. And these are called piecewise functions, and that's what we're going to look at in this video. What exactly is a piecewise function? How can we evaluate it when different inputs require different processes? And how can we graph these? So what exactly is a piecewise function? Well, it's a function that's defined by at least two, so two or more expressions or equations, each with their own specified domain. So for instance, here we have f of x equal to 2x in the case that x is less than 0, and 1/2 x in the case that x is greater than or equal to 0. So depending on what value we plug into this function will determine what process or what equation that we use to get the output. So for instance, here we have f of -6, and if we plug -6 into our function, well, we have to now decide, do we evaluate this at 2x or do we evaluate this at 1/2 x? Well, we know that 2x is going to be evaluated if we have x less than 0, and 1/2 x is going to need to be evaluated if we have x greater than or equal to 0. And in this case, -6 falls in this portion of the domain, right? -6 is less than 0. And so we're going to use that 2x that corresponds for that part of the domain. And so in other words here, we have f of -6, which will be evaluated by 2x, or equal to 2 times -6. And of course we can do the arithmetic here. When we multiply 2 times -6, we get -12, and this would be our final result. In other words, the input of -6 is evaluated on this top portion because it fits into that domain, and then gives an output of 2 times that input, which is 2 times -6, or -12. The input of -6 gives the output of -12, and we use that specific piece, the 2x, that's defining our function over that portion of the domain. Now on the other hand, if we wanted to evaluate f of +6, we have the same function here, which is 2x if x is less than 0, and 1/2 x if x is greater than or equal to 0. Well, in this case, this +6 fits the criteria that x is greater than or equal to 0, right? It falls in that piece, it falls in that part of the domain. And so we're going to use this function here, or this equation here, to evaluate and process the input. And so what we can say is that f of +6 is going to end up equaling 1/2 times x, or 1/2 times 6, which we can evaluate to be 3. And so when we plug in the negative value, we're using that top piece because that's less than 0. And when we plug in the positive value, we're using the bottom piece because that is greater than or equal to 0. And so when we input the value of 6, we're going to get the output of 3. And so evaluating these functions basically comes down to identifying what piece of the domain that your input falls into, and then using the corresponding equation to do the computation to get the output from there. And so we can take that same idea, now that we have an understanding of how to evaluate these, and graph them by the same process that we did when we graphed functions previously. We can plot the points. So if, for instance, we take the function f of x, which is equal to -2, if x is less than or equal to 1, and equal to x minus 1 when x is greater than 1, we can pick some values like -3 to 3 and all of the integers in between, and plug those into our function, evaluating them for the specific equation on that specific domain to give us the same types of coordinate pairs that we've worked with previously. For instance, if we look at f of -3, that's going to be less than or equal to 1, and so we would plug this in to this expression here. Now, you'll notice that this expression here is just a whole number and doesn't actually depend on x, so here we're just always going to have that output of -2, but this still gives us a way to plug in our input and get our output to give us a corresponding coordinate pair. In this case, -3, -2. And we can apply this in the same way to all of the values that fit this portion of the domain. So all of the values that are less than or equal to 1. And so what we can do here, just to kind of simplify our process, is go ahead and make note that everything above this line is going to utilize that top piece of our function, and everything below that is going to utilize the bottom piece. And so continuing to evaluate this, we have f of -2 that also gets evaluated based on the top piece here, and so we also have -2, giving us the coordinate pair -2, -2. For f of -1, we also evaluate that using that top piece, and so we get -2, giving us the pair -1, -2. And we could continue in this way for the remaining two. F of 0 is going to be -2, f of 1 is going to be -2, and so we have 0, -2, and 1, -2. Now, for all of the values that are greater than 1, we're going to have to use this bottom piece of our function, right, the x minus 1. So now when we plug in an input, say like 2, which is greater than 1, we would have to plug that into the equation x minus 1. So here, when we evaluate f of 2, that's going to be 2 minus 1, or 1, giving us the coordinate pair 2, 1. Or 3, which we would evaluate as x minus 1, or 3 minus 1, equal to 2, giving us the coordinate pair 3, 2. And then almost just like before, we can go ahead and plot these points and connect the dots to form our graph. And so we have -3, -2, we have -2, -2, we have -1, -2, 0, -2, and 1, -2. And then we have 2, 1, and 3, 2. We can draw a line here to connect the dots in this bottom section. And we can similarly draw a line to connect the dots for this top section. There's just one thing that we have to be careful of. Right, this function here switches at x is equal to 1. Right, it goes from being evaluated at the -2 to being evaluated at the x minus 1 piece. And so what we're going to have to do is graph this accordingly to account for that. Now, we already talked about in the last video how if we have a closed circle, that's going to represent including the value. And so that's when we see like a greater than or equal to sign or a less than or equal to sign. And then an open circle to represent not including the value, which is represented by just a less than or greater than sign. And so if we look up here and we see the less than sign here, that's going to indicate that we're going to need an open circle. And when we see the less than or equal to sign here, that's going to indicate that we're going to need the closed circle. And so we've got the closed circle here, but at 1 we have to make sure we put the open circle, right? And so what we're going to do here is follow the same trend of this line all the way to 1 and leave our open circle here. And then we can extend this out with an arrow in this direction. Now you might be wondering, why do we have that at all? Why don't we just start at 2? And this is a good time to remember that, yes, we're plotting these numbers based on some integer values, but we could also plug in fractions and decimals into this and get all of the numbers as close as possible to 1, right? We could plug in 1.00000001 into this function, and that would evaluate along this line here. But we can't include 1 itself, and so we're going to leave the open circle there. So that's why it's going to require more than just using the integer or whole number values. But hopefully that helps explain a little bit about piecewise functions. More or less, they're just ways that we can define a function by different equations or different expressions over different parts of the domain. But otherwise, we would evaluate them and graph them exactly the same way for their respective pieces. As always, if you have any questions, please reach out and let me know. I'm happy to help. And otherwise, I hope you have a great rest of your day.